I'm from the Institute for Disruptive Studies, and I'm going to talk to you about some tricks for defeating SSL in practice. So I've been talking about SSL for a little while now. So while I actually hate to repeat myself, we're going to start with the old and eventually come to the new. The backstory is a little bit important. So for me, the concept, I've been talking about SSL starting with the idea of certificate chaining. So normally when people think about certificates, they think about certificates as coming in pairs. They think about a site certificate, something like a certificate for PayPal.com that identifies a particular site, and then a CA certificate, which certifies that this site certificate is authentic. Sometimes the picture is a little bit more complicated. Instead of just two certificates, you might have more than two. It's this idea of having intermediate certificate authorities. The idea itself makes sense. Maybe your trusted party would wish to delegate signing authority to a third party, but that third party doesn't have their certificate embedded in your web browser and trusted. And so what they do is sign the third party, which then signs the site certificate. So you have this chain. The chain can be longer than 3. I don't know of any standard that says what the maximum chain length should be. I think it's implementation specific. I think that Firefox's limit is 25. So you could have 25 of these things in here. So then the question is, well, how do we verify these things? If someone hands you one of these certificate chains, what do you do? And it turns out that almost everyone tells you the same story. They say, you start with the leaf node, and you verify that the name on the leaf certificate is the same as the site that you're trying to connect to. Then you verify that it hasn't expired, and you check its signature. And if the signing CA is in your list of root CAs, you stop. Otherwise, you move one up the chain and repeat. So the problem, this is an image from IBM's website today. And they tell you the same thing, that you just sort of iterate through these certificates in this way. The problem is that it's very tempting to use a recursive function to verify certificate chains in this way. I find that when looking for security vulnerabilities, a good place to start is where the people who are implementing software might not understand the full scope of what's going on, and yet feel really good about the solutions that they implement. So in this instance, it's very tempting to use recursion, and someone who's implementing this might say, yeah, I did this with recursion, and it was recursive, and it was the function called itself. But the problem is that a sort of naive attempt at validating in this way is that you end up with a chain that is complete, but nothing more. And here's what I mean by that. So what if you have this picture, which is a very common scenario, right? You have your CA cert, a couple of intermediate certificate authorities, and then you have a leaf node for thoughtcrime.org, which is a domain that I own. So I have this certificate that's legitimately signed. What is to stop me from doing this? Creating another certificate for some other domain, like PayPal.com, and signing it with my certificate. If you go back and you look at what people say about how you verify these certificate chains, we haven't really done anything wrong, right? Like, the name on the leaf node is still the same as the name of the site that people are trying to connect to, PayPal.com. It hasn't expired because we created it with a valid expiration date. And if you follow the signatures, you eventually get up to a certificate that is embedded in the web browser and trusted. But, But we just created a certificate for PayPal, and we're not PayPal. It turns out that the missing piece is a somewhat obscure field called basic constraints. And the idea is that all certificates should not be able to do all things, right? Some certificates should just be for identifying end entities. Some should be for key revocation, and some should be for acting as certificate authorities. And so these constraints basically say what a certificate should and should not be allowed to do. The problem is that back in the day, when most certificate authorities issued certificates, they would just leave this field out. It just didn't exist in the certificates that they issued. And you would think that if you were like writing an SSL stack, if you just didn't see that field, you would assume that this is not a certificate authority certificate. But in reality, whether the field was there or not, most SSL implementations didn't bother to check it. So what this meant was that anyone with a valid leaf node certificate for any domain could create and sign a leaf node certificate for any other domain. And when you presented this chain to Internet Explorer, Outlook, Conqueror, OpenSSL, and many others, it would accept it as valid. So then one day, back in 2002, Microsoft did something particularly annoying, and I blew this up sort of in response by publishing it. Microsoft claimed that it was, okay, this is a real vulnerability, but it's basically impossible to exploit, so I'll also publish the tool that exploits it. The tool is called SSL Sniff. It works like this. You have an SSL connection between a client and a server. Let's say the client's trying to connect to PayPal.com, and SSL Sniff will man in the middle of the connection. So you intercept the client request, and then you just do this trick that we've been talking about, where you intercept the client request, and you generate a certificate on the fly for the site that the client is trying to connect to. So if they're trying to connect to PayPal, you create a certificate for PayPal, and then you sign it with any valid certificate. So if I can legitimately get a certificate for thoughtcrime.org, I just sign it with my thoughtcrime.org certificate, and then I pass it back to the client. Simultaneously, on the server side, you just make a normal SSL connection to the server. The server doesn't know that anything is amiss, it just got a normal SSL connection, and then you just pass data back and forth. So the result is that the client doesn't know that anything is amiss, the server thinks that everything is fine, everything is really encrypted except for where you are, where everything is decrypted in the middle, and you can log it or modify it or do whatever you'd like. So then the question is, sort of post-disclosure, is this tool still useful, SSL Sniff? So first, you'd be surprised who still doesn't check basic constraints. Still happens. The second thing was, for a while, even when people got warning dialogues in their browsers, they would just click through them. And there was actually some interesting stuff that you could do where, like, they would, so for a while, browsers would start validating the certificates that they saw, and as soon as they found an error, they would stop and be like, there's an error, this is what it is. Do you wish to continue? And like, if you look at the order that they do things, the first thing that they do is verify that the name in the certificate is the same as the name of the site that they're trying to connect to, and then the next thing that they do is make sure that it hasn't expired. So you could create these certificates with just bad signatures, totally bad signatures, and have it expire like 2 minutes ago. And the client would get the certificate, and it would check the timestamp, and it would be like, there's something wrong. This expired 2 minutes ago. But they would fail to mention that the signature was completely bogus, and all these other things. And so users would see that and be like, well, it only expired 2 minutes ago. It's not that old or whatever, and they would just click through it. And then, so lastly, it's still sort of useful as a general tool for attacking SSL. It's easy to kind of extend it for other purposes. For instance, the people that did the MD5 hash collision stuff last winter eventually got a rogue CA cert. And they were able to deploy that using SSL Sniff, because once you have the CA cert, to use it, you still need to sort of sign and present certificates to clients that are trying to connect to places. And if you run SSL Sniff in this normal old mode and you hand it a CA cert, it just works perfectly, right? Where on the fly it'll generate a certificate for the site that the client is trying to connect to, sign it, and pass it back. And then there's some other uses yet, which we will end up talking about. But so then, then I started thinking, okay, in this case where we're just sort of, asking users to click through these dialogues, like surely we can do better than this, right? So lately I've been talking about this concept of SSL stripping. So I've been talking about this a lot recently, so I'll try and be sort of brief here. But SSL stripping is fundamentally about bridges. So SSL is useful, but how it's deployed really matters. And sort of my thesis here is that it's deployed on the web in a kind of strange way, where, for instance, I posit that people rarely encounter SSL directly, that it's very unusual for people to type https:// into their web browser. That instead, I feel like people encounter SSL on the web in one of two ways. Either through redirects, so you type bankofamerica.com, enter into your URL bar, and the browser sends a HTTP request to bankofamerica.com. And bankofamerica.com is an all SSL site, so it responds with a 302 redirect and a location header that says, no, please reconnect to https:// bankofamerica.com. And so that's how eventually you get to the SSL. Or through clicking on links. So users are browsing along, and eventually they come to a link that says, my shopping cart, or checkout, or sign in, whatever it is, and they encounter SSL that way. Both of these points are bridges. Bridges between a secure and an insecure protocol. And so they're actually very weak links, and they're attackable. So the idea here is that we can attack SSL before we even get to SSL. So in the past, we've had this tool SSL sniff, and it tries to man in the middle the SSL connections directly. And instead, we're talking about a new tool that I've written called SSL strip that instead attacks HTTP. It does man in the middle attacks on unencrypted communications. And it works like this. It does a man-in-the-middle attack on all the HTTP connections on, say, a LAN or wherever you can get. And it watches all the HTTP traffic go by. Then it watches for these two bridges, right? The links and the redirects. So whenever it sees a link to a HTTPS URL, it just swaps it for an identical URL that's HTTP. And it keeps a map of what it's changed. So it remembers that this was supposed to be a secure link. And then likewise, whenever it sees the location headers, these are what will be in the 302 redirects that come back from a web server. If it sees a location header with a HTTPS link in it, then it again just swaps it to an identical HTTP lookalike, and it keeps a map of what it's changed. Then it keeps watching the HTTP traffic go by, but whenever it sees an HTTP request for a URL that has been stripped, like a URL that should have been an SSL connection, it proxies that out as HTTPS to the server. And then you keep watching the HTTP traffic go by, and anything that you come back that from the secure link that has relative links in it, CSS links, JavaScript links, or whatever, you keep a map of those as well, because those should also all be proxied out as SSL to the server. So the upshot is that, get to that. The upshot is that the server never knows that anything is amiss, right? It's getting SSL connections for the URLs that it wants to get SSL connections for. And the client doesn't show any warnings or errors. It just never gets upgraded to SSL. So how does this look, right? Here's Gmail's login. So this is the normal secure version of Gmail's login in Firefox 3. And this is the strip version. It's pretty subtle. Here's the same page in Safari. So this is the secure version. This is the strip version. The only difference in Safari, I'll show you again, is if you look in the top right corner, there's a little blind embossed padlocked icon. That is the only thing that disappears. That and the S. The S doesn't actually show up in the URL bar anymore. So I've been talking about sort of the evolution of how web browsers have made us feel in terms of security, right? And that I think that there's been this evolution from positive feedback, where web browsers are deploying this sort of plethora of icons and URL bars that turn gold and all this crazy stuff to tell us that things are secure, instead to a place where web browsers are focusing more on negative feedback, where they've toned down all of the positive indicators. There are less little lock icons, the URL bar doesn't turn gold anymore, and instead they've really ratcheted up the errors. It's not just a dialog box that you can click through anymore. It's a whole page that renders out this thing, right? So no one's going to click through this. And so my thesis is sort of that, like, most people's usage patterns is to just continue along until they get something that tells them that something is amiss, right? That as long as they don't see this, that no one will really notice that anything is different. The sites themselves confuse us, right? Like, so here's PayPal. And they have like their own lock icon on the page, you know, and they say it's secure and all this stuff, whatever. They don't really know, right? There's other weird patterns on the internet, right? Like, so this is Wackovia's, it's a bank in the United States. This is their website, and this is their normal website. This is how it looks when you go to their website and you haven't been attacked, right? And the idea is it's this HTTP page, and then you're supposed to type in your credentials on the left here, and when you click login, presumably that will post to an HTTPS link. And again, they have their own little lock and everything or whatever. So this is what the secure version looks like, okay? And this is the strip version. I'll show it to you again. Secure version. Strip version. Right? So there's no way to know, right? And since this is a button, when you mouse over it, it doesn't show you the post target in the status bar down there. So there's really no way to know that you're being attacked. This pattern is everywhere, right? So it's hard to determine what's going on. Here's E-Trade. These people are really crazy. They've integrated the lock icon into the actual button that you are supposed to click, right? So, you know, is this the secure version or the strip version? Does anybody have a guess? One for stripped? The source. So this is another interesting thing, right? The best you could do is maybe to look at the source and see whether this is going to post to a secure link or an insecure link. But it's actually an imperfect solution, because when you view the source, the browser actually makes another request to the web server to get the source and display it. So what you view as the source is not necessarily what's rendered on your screen. So this is the strip version. This is supposed to be HTTPS up at the top, but there's no, you know, it's hard to tell, right? What's it supposed to be? And then SSL strip does other little tricks where you can have it replace the favicon with a little lock, just because people like the lock or whatever. It also does stuff like it'll kill sessions if you ask it to. So, because one problem is if you want to be intercepting people's traffic, you really want their like login credentials. So it will actually kill their session if they have a long-running session, because otherwise you would miss the login step, you know, because they would have the cookie. You could get the cookie, but that's not as good, right? So it'll kill the sessions and stuff, so you can get the login credentials. Anyway, so I've talked. There's a lot more. There's a lot more here. That this idea of attacking this bridge between HTTP and HTTPS is the fundamental idea, and just stripping the SSL out is kind of the first thing you can do. There's actually like a whole ecosystem of attacks there that are pretty cool, and I've talked about that a lot before, so I'm going to move on. So then the question is, all right, we've got this SSL stripping thing, so where can we go from here? And really, for me, the larger question is, where do we need to go from here? Because in reality, the SSL stripping thing is deadly. It never fails. I published some statistics that I collected from a Tor exit node, running SSL strip on a Tor exit node, and they're pretty crazy. Basically 100% success rate. I've run this at HackerCons, including this one, and had surprising success rates as well. So it's not even just a matter of user education, that there's something else going on here, and people are often fooled by this. So this is deadly in itself, right? So the question is, where do we need to go from here? And I think, so for me, there are a couple of places, right? One is that some people do type https://. Some people have started using bookmarks for their secure sites so that they don't expose themselves to this bridge, right? And then the other thing is SSL is used for many other protocols, right? SSL is used to protect, SMTP, POP3, IMAP for VPN stuff, right? And these protocols don't really expose this bridge. So we need some other tricks. So the first question is, like, what's up with certificates, really? People talk about certificates a lot. What's really going on? They're actually quite simple. How they have been designed is a little bit more complicated, but they're just supposed to do something pretty simple, right? Where a certificate identifies a subject and provides that subject's public key. And it is given out by an issuer, and it is known to be valid based on that issuer's signature. So really, that's all the information that a certificate is trying to convey. This is what a certificate looks like. This is OpenSSL's printing of a certificate this is Google's certificate. So you can see the subject is Google, and there's the public key in there. It's issued by Thought, and there's a signature, Thought's signature of the certificate. So what SSL is ultimately trying to provide is the big three: secrecy, authenticity, and integrity. You need all three to have a secure protocol. Most people, when they think about like encryption and stuff, they think only about secrecy. But if you don't have authenticity and integrity, as we'll see, you do not have a secure protocol. SSL is using these certificates to get authenticity. So the client, the sort of basic dance sort of starts with the client connecting to the server. So let's say the client's trying to connect to PayPal again via SSL. The client sends this client hello message, and the message basically says, hello, I use SSL version whatever, I support these cipher suites, here's a random number, a few other bits of information. And the server responds, yes, hello, I also support SSL version whatever. These are the cipher suites that I like. I think we should choose this one. We should use this compression method. And by the way, here's my certificate. Now, as soon as the client gets the certificate, the first thing that it's going to do is look at the subject. And it's going to make sure that the subject is the same thing as whatever you typed into your URL bar if you're using a web browser, whatever you typed into for your IMAP server if you're using a mail client, whatever IRC server you're trying to connect to if you're using SSL for IRC. So this is really where the problems for us as an attacker begin, right? Because we can intercept the client hello and we can read it just fine, and we can send back our own server hello that says, yes, I am the server, whatever. But we have to send a certificate. And what do we send? We can't send the real certificate because that has the server's public key in it and we don't have the corresponding private key. And we can't send a certificate that says thoughtcrime.org because the client will compare that against what they're trying to connect to and say, well, I wasn't trying to connect to thoughtcrime.org, I was trying to connect to PayPal. So what do we do? All right. We can think about solving this problem by, again, looking into the past. So in 2000, things were different. When I was getting certificates for this basic constraints vulnerability, I was just trying to get, a certificate for my own domain that I owned, right? And it was very different. There were notaries involved. Notaries in the United States are these people that work for the city and they authenticate that you are you, and they have seals and stamps and they cost money and stuff. There was identification. I had to actually provide state ID. I had to talk to people on the phone. There were actual people involved. I remember at one point talking to this guy at VeriSign who was grilling me. Like, he was really, giving me the third degree, and I actually remember thinking to myself, my God, how am I going to prove to this guy that I am me? I wasn't even trying to fake him out. I was just like trying to get a real certificate for me, right? And it was tough. But that is a bygone era. These days, it's all about this thing, online domain validation, right? So this entire process has been replaced with a website. So you go to the website of a certificate authority, and there's just a form where you submit your certificate signing request. And it's a fully automated process. A certificate signing request is just another little data structure that looks like this. It's defined in this standard called PKCS number 10. And again, it's pretty simple. There's a version, your public key, and our old friend, the subject. This is the value that is going to be put in the certificate that gets issued. Whatever is in here is going to end up in your certificate. So presumably, we'd like it to say something like bankofamerica.com, right? If we submit a certificate signing request with a subject of bankofamerica.com to VeriSign or Thought or any certificate authority, they are going to look at the root domain. They're going to do a whois lookup, and they're going to pull out whatever contact information is there for the administrative or technical contact. Maybe they'll send them an email, make a phone call, whatever it is. The important part here is that they only look at the root domain. They don't care about whatever subdomains you're trying to get. They don't give a shit about what that says. It could be anything. It could be certificate authorities are a total ripoff.bankofamerica.com. If you submit that, you're not going to offend anybody. No one will even see it. They will dutifully ignore that, look at the root domain, and do this whole whois lookup. All right, so I've been oversimplifying this situation just a little bit up until this point. Subjects are not just like a string with a URL in them. They're actually this whole other structure called a distinguished name. To understand this structure, you have to understand that X509, which is the standard which defines all of the certificate stuff, is a total nightmare. It's been through 3 revisions over 20 years. Parts of the standard have literally been lost and then found again. I'm not kidding. When the 1988 standard was being updated to the 1991 standard, whoever was just copying and pasting it over just forgot to copy part of the section of the standard over, and then that got published as the standard. And then people implemented implementations based on what got published, and then they were like, oh shit, we forgot the thing that, And so then they redid it, but people had already implemented stuff based on what had been out. So it's like when you look at how to implement SSL, it's the kind of thing where it's you get the standard, and then you get the user's guide for the standard, where it's this is what the standard says, but really in 1991 they did this weird thing, so what you do is you check for this value, but if it's not there, that's okay, even though the standard says it has to be there. And then you look for this other thing, and if not, then you try this. It's out of control. So the original vision for X509 was that there would be these things, distinguished names, and each distinguished name would fit into some kind of global information directory tree. So everything would exist hierarchically, right? I would get a certificate, and it would say country, United States, state, Pennsylvania, locale, Pittsburgh, organization, Institute for Disruptive Studies, organizational unit, research and development, common name, Moxie Marlinspike. But in practice, the standard is very weak and everybody does everything differently. Usually people get to locale when they're filling this out, and they say, what the fuck is a locale? And type whatever they want. This basically, so one of my favorite quotes is from this guy on this mailing list, and He says, there's nothing in any of these standards that would prevent me from including a 1 gigabit MPEG movie of me playing with my cat as one of the RDN components of the distinguished name in my certificate. And the thing is that he's right. You know, you really could do that. So in the end, when SSL is dealing with X509 certificates, SSL implementations just ignore everything but this common name field. And in the common name field, instead of putting like your name, like Moxie Marlinspike, you put your domain. So if this certificate is supposed to be used for www.bankofamerica.com, that's what you put in there. And everything else is just ignored. So how is this common name represented, right? So in memory and in the certificate, it's defined like this. So it's X509 uses ASN1. So we have this ASN1 notation. And the common name is basically just a sequence that identifies it as the common name, and then a string type. And there are many different string types in the X509 standard. But if, for instance, this is just an ASCII string, then you would use the IA5 string. So an IA5 string looks like this. It's a tag length value where you have 1 byte ID that says this is going to be an IA5 string, 0x16. Then you have a 1 byte length character that specifies the length of the string to follow. So in this case, you would have 0x5, which says that there's going to be 5 characters in the string. And then the next 5 characters are the actual value of the string, 1 byte per character. Pretty simple. So what's interesting is that this is essentially a Pascal string, right? Where, I don't know if people remember, but Pascal stored strings this way, where like the first byte of the string was, or first one or several bytes of the string were the length of the string to follow. So, if we were going to write PayPal.com, we would have, the 1 byte length and then the actual string. So this is different from how C strings are represented. The C programming language uses null characters, where instead of like knowing how long the string is, you just get a pointer to the first character, the W, and then you just have to like keep iterating through memory until you encounter a null character, and then you're like, oh, I'm at the end of the string. This is how long it is. So these are sort of different. The important thing to note is that with Pascal strings, a null character does not have any special meaning. It's not imbued with any special meaning. It's just another character in your character string. Doesn't mean anything else. So, in our case here, we would like to get a certificate with the common name of www.paypal.com. The problem is that we don't own paypal.com, so when they do this domain validation stuff, we won't get the email or whatever. But what we do own is thoughtcrime.org. So now remember, they only care about thoughtcrime.org. They don't care about any subdomains, right? So I can get www.thoughtcrime.org, verisineedschildren.thoughtcrime.org, even things that don't exist, I.thoughtcrime.org. It doesn't matter whether it resolves or not. They don't look at it at all. They just totally ignore it and look at the root domain. So I could even get a certificate for www.paypal.com nullcharacter.thoughtcrime.org. When I issue a certificate signing request for this, they will dutifully ignore everything, look up thoughtcrime.org in the Whois database, and contact me. So now we have some intuition of what we might want to send back to this client in this sort of dilemma that we're in, right? So we get the client hello, we send back server hello, and we try sending back this certificate, www.paypal.com nullcharacter.thoughtcrime.org. As soon as the client gets this, they're going to want to compare, again, what they are trying to connect to, paypal.com, to the subject in the certificate. That code might look something like this. Char destination is get domain we're connecting to, char common name equals get common name from certificate, and then if everything is okay, those two will be the same. Right? So the way that like a standard C string comparison will go is like this. You have pointers to the first character in both strings, and the comparison function will look at the two first characters and say, are these the same? If they are, then it will check the next two, and then the next two, and all the way to the end of the string. And when it sees the null character, it's going to say, okay, well, this is the end of the string. And it's going to return success. So, in the eyes of most SSL implementations, this certificate is completely valid for www.paypal.com. So what are most SSL implementations? Pretty much all of them. So web browsers, Firefox and is vulnerable to this attack. And it's still vulnerable. There hasn't been a patch yet. So this is still exploitable on basically all Microsoft products. Like Chrome is still vulnerable because it runs on Windows and it uses the Microsoft Crypto API. So it gets sucked into this. So Chrome is still vulnerable. Links in curl, those were vulnerable. So mail clients, again, like all of the Mozilla stuff is vulnerable. Thunderbird, SeaMonkey, like all the Mozilla products are vulnerable because they use the same SSL stack. So Thunderbird it got patched at almost the same time as Firefox. But Outlook is still vulnerable. Evolution was vulnerable because it uses NSS, which is the underlying SSL implementation for the Mozilla products. And I don't know. I assume that they've rebuilt that with the new patched NSS. All this other random stuff, like the bunch of chat clients who are vulnerable, Pigeon, AIM, IRSSI, Center ICQ. I don't know where they are in patching their stuff yet. And then like all the SSL VPNs were vulnerable too. AEP, Citrix, all that stuff. So I updated SSL Sniff and to support this attack, right? So it basically supports null prefix certificates, right? So you can invoke it and you hand it a bunch of null prefix certificates and it does its normal like man in the middle on a network, and if it sees a connection for a site that it has a null prefix certificate for, it will hand that back to the client and do the man in the middle attack. Okay, so how does this look? So this is Gmail's login, Firefox 3 again. This is the normal version, and this is the attacked version. There's literally no visible difference, nothing, right? And even if you were to look, even if you go to inspect the certificate, everything looks fine because again, whenever it tries to display this string, it gets terminated in the same way. So it always displays the same, and nothing looks amiss. So what are some disadvantages to this attack, right? For me, the big disadvantage is that I don't like targeted attacks. I think targeted attacks are kind of lame. I think phishing is too much work. I don't want to have to get a certificate for every site that I want to potentially intercept communication for and then try and get the people to go to the site and all that stuff. I just want to man in the middle of the network and get everything on the network. All right, so maybe there's some trick in there somewhere that we can exploit to get all the data, So, a good first step might be to look at the code for, like a client that implements SSL and check, how it compares the names and stuff like that, right? So we can look at the NSS, which is the Mozilla code. And so don't look at it too carefully, let your eyes go out of focus. And just look at the shape of it. This is the function what they use to compare the strings. just without even looking at a line of code, just the shape of it looks wrong, you know? It's like, it has all these nested conditions, like weird for loops in it. It's too long, for one. I mean, it goes on for like another 3 pages. So without even looking at a single line of code, you know there's a bug in here somewhere. So then your eyes start to clear. And you look at the very first line. Register int xy. Register int xy? How old is this code? Compilers have ignored register shadowing for 10 years. You know, it's like, this is like 14-year-old code. So that's another bad sign. So certificates, you can get wildcard certificates. You can get like star.thoughtcrime.org and then, you know, www.thoughtcrime.org or mail.thoughtcrime.org. It all matches. So you look at the wildcard case, and it, like, apart from just being the least inefficient way to implement this that I can imagine, it has some other problems, or idiosyncrasies, I guess, where you can get a certificate for star null character.thoughtcrime.org, and it, yeah, it's funny. So it will, it just, you know, it becomes star, and then that matches everything. Any string that you compare it to, it matches. And there's other weird stuff in there too, where like you could get, if you don't want to use a null character, you could get star tilde.thoughtcrime.org, and that would work. And then it also supports grouping. It's like a full regular expression support. So you can get like, if you don't want, because a wildcard certificate costs a little bit more than just a normal certificate. So you could like, if you don't want to shell out for the wildcard certificate, you could just get, you know, paypal.com or mail.google.com or eTrade.com or Bank of America or, and any of those will match. And there's a remote exploit in there too, or I don't know what you call it, local remote something, where when in the grouping support, it like allocates a string based on the length of the string, which will terminate the null character, but then it will happily copy until it sees a closed paren. And so it's classic overflow. You submit something like this, and it allocates this much memory and copies that much memory. The star is actually really aligned to make this exploitable. That should be like a whole other talk, but like time after time, like going through this, it's like, okay, but you can't get the shellcode past the Unicode filters, right? And you're like, no, you can. It's, you know, and then you're like, well, the nested conditions aren't going to work, and then it does. And so the star's really aligned. And the nice thing about this is that like no signature was required, right? Because you could pass this to a client and it would check the subject before it would check the signature. So you don't even have to get your exploit signed. Like you just create a certificate, shove this in there, and then you pass the thing to the client, and it'll trip over it. And since this was an NSS, it'll work for all this other stuff too: Evolution, Pigeon, AIM, Thunderbird, all that stuff. What? Oh, in the new versions of the Mozilla products, it's fixed. I don't know about AIM or Pigeon or Evolution, but probably they fixed it. I don't know. Probably. So, what? Yeah, I don't use that. Okay. So, right. So now there's a new version of SSL Sniff in this evolution where we do the normal attack with the null prefix certificates, but if we have the universal wildcard certificate, it'll automatically just use that on any NSS clients. So basically, SSL Sniff has to fingerprint the network, so it fingerprints the network and figures out what clients are vulnerable on what level, and it exploits them accordingly. And then if they're non-exploitable clients on the network, it's just left alone. They're just left alone so that there's no detection or suspicion. So what do we have to worry about as attackers? The two big things that come to mind for me are certificate revocation and updates, right? So it would be unfortunate if some bidder certificate authority were to go back and look at all the certificates that they've issued and discover that many were issued with null characters in them and revoke all of those certificates. It would be just as unfortunate if some bidder SSL implementation fixed all their products and then our like fun tricks didn't work anymore. So, certificate revocation. These days it's all about this thing called Online Certificate Status Protocol, or OCSP. So the deal is that like in a more complicated world now, like the old methods for revoking certificates weren't scaling very well. Like these certificate revocation lists get really, really big, and each certificate authority has one, and there's just so many certificates in play and being revoked now that they're hard to manage. So people wanted this, this other solution, and what they came up with was this thing called OCSP, and it's like supposed to be like this really lightweight online protocol. So whenever an SSL stack sees a new certificate, like if you are using your web browser and you go to Google, when the certificate comes down, the web browser will do a quick check to the OCSP provider for that certificate and say, hey, is this certificate still valid? And the provider will either say, yeah, it's cool, or no, we revoked that. And if it's been revoked, then the web browser will be like, whoa, whoa, to the user, there's something wrong, this is a revoked certificate, something is amiss, which is bad for us as attackers. So you can see, like in Google's certificate, there's the OCSP URL that's embedded in the certificate. So the browser will connect to ocsp.thought.com and check. So this is enabled by default in most browsers, and this happens automatically just as you're going along. So we should start looking at OCSP probably to see if there's like some tricks that we can do with that to avoid these problems. A basic OCSP response looks like this. So the client will issue a request, and none of this happens over SSL. This is a different protocol. The client will issue a request, and the server will send back a response. The response looks like this. There's just a simple status, like success or failure or whatever, and then the actual response data that comes with it. And the response data is optional based on what the status is. So the response data looks like this. It basically includes like the certificates for the OCSP provider and like elaborates on exactly what the status of a certificate is. And the thing that's troublesome for us is that it's signed. So it's signed by the CA, which could be difficult to forge. Could be difficult to forge that signature. But the interesting thing is that everything is not signed. In fact, only this is signed. Just the actual response data itself is the only thing that's included in the signature. All this other stuff is not signed. It's not included in the signature. So notably, the status is not included in the signed response. So, all right, what are the statuses, right? These are the possible status values. You can send success. And if you send success, you have to include the response data. So we can't really send success because then we would have to forge a signature, and they're not replayable very easily. So we would have to forge a signature, and that can be hard. So we can't really send success. Malformed request. Well, we don't really want to send that. That doesn't sound good, right? Internal error. Probably don't want to send that. It includes the word error, and that's not good. Try later. That doesn't sound that bad. It implies that there could be success, right? Like at a later date, it could be successful, right? It doesn't sound that bad at all. And when you send the try later, you don't have to include the response data. So all you have to send is the status, and you don't have to include a signature. So you just send back 3. And it's really, it's not even like a short. It's just like the ASCII character 3, like 0x33. That's all you have to send back. And most SSL implementations also agree that it doesn't sound that bad. And actually, every SSL implementation just basically treats it as a successful condition and continues otherwise. which means that this entire protocol, OCSP, can be defeated with the number 3. So all you have to do is intercept the OCSP request, which is not hard at all if you're already intercepting their data, and send back 3. So I see that I'm almost out of time, or that I should be stopping. So I'll zip through the rest of this, but... all right. Okay. All right, well, I don't set the... whatever. Anyway, so SSL sniff now supports the OCSP denial. So basically what it'll do is it does everything like before, fingerprints the network, attacks clients as necessary, and then optionally it supports a parameter where you can have it watch for the OCSP requests corresponding to whatever certificates we're using, and if it sees an OCSP request for a certificate that we have that's forged, it'll just send back 3. And that's it. Okay, so the other thing that we have to worry about is updates. And so it used to be that people like downloaded and installed software, but that's sort of changing. Software has gotten more complicated and the stakes are higher. So vendors have tried to like employ methods to get software sort of patched more quickly. And so a lot of people are using the self-updating software. So, you know, vendors are going to be able to patch these bugs pretty quickly. So that's bad news for us, because by, you know, giving all these tricks away, vendors are going to patch the software. But it seems like the update mechanisms themselves are potentially dangerous, right? So maybe there's something that we can do. So when you install Firefox or Thunderbird or any of the Mozilla products, it comes with the automatic update service, which is a feature that's enabled by default. And it works like this. The browser or the client or, you know, whatever it is, makes an SSL or TLS. When I say SSL, I really mean TLS. It's just that when I say TLS, nobody knows what the fuck I'm talking about. So I'm just going to say SSL. Nothing is SSL anymore. It's all TLS. Anyway. So the browser makes a SSL connection to the automatic update server, and it says, hello, do you have any updates for me? This is my product, either Firefox or Thunderbird or whatever. My version number, my build ID, operating system, Windows NT, Linux, OS X, locale, you know, English, Spanish, and channel, nightlies, production, whatever. And the update server in the sky just says, as a matter of fact, I do. Here is a totally unsigned blob of data. Please run this. And the client does. And the deal is that they're relying on this SSL connection to protect them against all possible attacks. So if we can intercept the SSL connection, we can send our own update responses, which means that we can get whatever code that we want to run on the client. By default, the like minor updates, like if you're updating from Firefox 3.0.13 to 3.0.14, those are just sort of like installed by default. Like without the user knowing anything, it like connects, starts downloading, and then once it's all downloaded and unpacked, it just pops up a dialog that's like, there's a new update, okay? And you click okay, and then you're running the new thing. So the update server is the one that reports what version is coming back down. So the update server is effectively, it's capable of deciding whether this is installed silently or not. And if we're posing as the update server, then obviously we can just send back something with a minor version update. So we can send back whatever we want. All we need is a universal wildcard certificate or a cert for aus2.mozilla.org. And we can send back rootkitted binary, something that hacks all, you know, redirects all the traffic. We can send back a completely legitimate image that just happens to include our own CA certs. So no one knows that anything is amiss, but in the future, our CA certs will be installed on some user base. Or just to be confusing, we can send back a totally different web browser. You could like get the update thing and restart, and it just, thank you for updating to Galleon 0.3 or whatever. So basically, the automatic update service is not very trustworthy. until they implement code signing. So now SSL sniff does this automatically for you. There's a command line option, and you can specify whatever binary you want, and it'll get installed on the thing. I'm sorry, I'm just going to rush through the rest of this, but just as a postscript, stripping null characters is not a solution. Like some browsers like Safari and Opera were doing sanity checks on the common names. And what they would do is strip the null character out of it and then do the compare based on the string without the null character. But they've exposed themselves to a different attack, right? So what you can do, some certificate authorities are internally vulnerable to this attack, where the certificate authorities themselves trip over the null character. So if I submit a certificate request to www.paypal.com nullcharacter.thoughtcrime.org, some certificate authorities will internally validate that against paypal.com, but then if that validation succeeds, I will get the full string in my certificate, right? So I don't have paypal.com, but what you can do is register a domain like sitekey.ba. So you register that, and then you get a certificate for sitekey.ba, null character, incofamerica.com. And so you submit that to a certificate authority that is internally vulnerable to this attack, and they'll validate that against sitekey.ba, but then they'll give you the whole thing, sitekey.ba, null character. And so when you later present that to a SSL implementation that strips the null, it becomes sitekey.bankofamerica.com. So it's a little bit more of a stretch because for every domain, not only do you have to register a certificate, but you also have to register a whole domain. Yeah. But it's whatever. It's a neat trick. So in conclusion, we've got a man-in-the-middle attack that will intercept communication for basically all SSL and TLS implementations. In the case of NSS, we only need a single certificate. We've defeated OCSP as implemented. We've hijacked the Mozilla Auto Updates protocol. Oh, and this works against extensions too, on add-ons. It's actually easier just to hijack the add-ons and send back a rogue add-on because you can basically do everything from the add-ons. And we've got an exploitable overflow. So in short, we've got your passwords, your communication, and control over the software that runs on your computer. That is all. Thank you.